Hello everyone. In this video, we will talk about inductor design, a precursor to inductor design. Before getting into the topic, I want to tell you all my videos are going to be of three types: absolute, applied and abstract. Absolute will deal with the basic and the fundamentals. Applied will deal with applied engineering, where we'll talk about design, where we'll talk about engineering and stuff. And abstract will be fun. We will let out our kid in front of this vast universe. We'll talk about physics becoming metaphysics and such stuff. This topic comes under applied. So let's get into the topic of inductor design. For anyone to design an inductor, you must intuitively know certain parameters about an inductor and its functioning. For this reason, I have divided this talk into three parts. First part is understanding an inductor as a device with its mechanical or visualized analogy. Second part is an electrical system and magnetic system analogy. Third is basic important equations and its relationships. For you to have the best takeaway from this, there are some prerequisites. They are basic understanding of energy, power, electromotive force, potential difference, current, resistance, Ohm's law, and basic mathematics and units. By definition, an inductor is a passive two-terminal electrical component that stores energy in its magnetic field when current flows through it. Here are some pictures of different types of inductors. And inductance is the inherent property of an electrical conductor to oppose the change of electric current through it. When current passes through a conductor, it creates a magnetic field around it, the direction of which can be found out by Maxwell's corkscrew rule. If the current is in this direction, the magnetic field created will be in this direction. Please remember that this direction poles are basically to standardize the study and unification of the understanding. These are like left and right, north and south, up and down, and negative and positive. Now that we know a magnetic field is created around a conductor when current passes through it, we utilize that principle by using certain winding techniques in order to make practically usable inductors. And SI unit of inductance is Henry. The direction of a magnetic field in a single straight cable and in a coil format follows this right-hand rule. If you carefully analyze this direction and polarity, you can see that they are additive when we wind it on a former as long as we keep the direction same. If we change the direction, the polarity also changes. Ideally, when equal numbers of turns are wound in opposite direction, the net inductance becomes zero. Michael Faraday is credited with the invention of the inductor. He not only invented the inductor, but also laid down the principles of electromagnetic induction and its mathematical equations, which were later augmented by Maxwell and other great scientists. We shall explore these important equations as we progress on this topic. In order to understand the functionality of an inductor from an electrical domain, I'm going to give you an analogy of a mechanical device, which is an inertia wheel. In the mechanical domain, you know that a moving mass can store energy in the form of kinetic energy, and the energy is given by the equation half mv square. M stands for the mass, v stands for the velocity. Same way, in an inductor, in an electrical world, an inductor can store energy as long as there is a current through that, a movement through that. And the equation for the stored energy of an inductor is given by energy is equal to half Li square. You can see that the mass is the equivalent of inductor from electrical domain to mechanical domain. And the velocity, what you're seeing in the mechanical domain, is the current or the movement of electrons in the electrical domain. In a mechanical domain, inertia is a property where a mass opposes any change of its velocity. If the velocity is 0, it prefers to be at 0, and if the velocity is at x, it prefers to be at x. In the electrical domain, in the case of an inductor, it tries to oppose any change of a current through the inductor. If the current through the inductor is 0, it tries to maintain it to 0. If the current is x, it tries to maintain to x. And this property is called inductance. If you give an input stimuli to an inertia system or to an inductor system, the resultant effects are going to be similar in nature. Let's give a step stimuli to both the system and check out how does it behave and what all are the analogy of the two. What it means by a step stimuli is that you are going to give a fixed amount of a stimuli for a fixed time. Let's give a tangential force onto this inertia device, a step stimuli, and let's check what's going to happen. Once you give a tangential force onto this inertia device, you can see that the inertia wheel starts rotating and it develops an angular velocity. So once you give a stimuli at this point t1, you can see that the angular velocity keeps increasing. And when you abruptly stop the stimuli, since the wheel has picked up certain velocity, angular velocity, it keeps rotating, and you can see that it tries to maintain its velocity and slowly starts ramping down at certain time interval. The maintenance of this velocity is because of the stored energy in the inertia wheel in the form of kinetic energy. In the case of a linear system, it is half mv squared, whereas in the case of a rotating system, it's half moment of inertia multiplied by omega square. At this point of damping down, or when the velocity comes down from v2 to 0, the force exerted by the inherent property of the wheel, and hence from the reference point of this inertia wheel, you can see the direction of the force is reversed. In the case of an inertia wheel, you have applied a tangential force. And let's look at in the case of an inductor. In the case of an inductor, what you're going to apply is an electromotive force, a motive force for the electrons, a force that is intended to move the electrons. So once you apply an EMF by closing the switch, you get a resultant current flow or a movement of electrons. Once you start applying this electromotive force, the current through the inductor starts ramping up from 0 to a higher value. At any given point of time, the energy stored in the inductor is given by an equation. Energy is equal to half Li square. L stands for the inductance value, I stands for the current. And when you abruptly stop this by means of the switch, you can see that I have provided a discharging circuitry, a path for the inductor to discharge. Just like in the case of this inertia wheel, where the wheel tried to maintain its motion, the inductor will try to push the same flow of current through the device, and it can create a force, a voltage in the opposite direction. Like the way this inertia wheel created a force, the inductor will create an electromotive force. It generates a voltage which is equivalent to this Zener voltage and the drop of the diode, and tries to discharge the inductor through this channel. It tries to maintain its current through this path, and the voltage generated by the inductor will be equivalent to the barrier voltage provided by these two diodes, which is Vz plus drop of this forward diode. And what you can see is, as the inductor discharges, the current through the inductor slowly comes down and ramps down to 0. Once the current through the inductor is maintained through this path, Since there is a barrier potential here, the current into voltage generates a power dissipation and the energy stored in the inductor gets discharged in the form of heat here. You can see in this graph, I have tried to represent two input stimuli of two different amplitude. You can see that in spite of the input voltage levels, the voltage generated by the inductor is equivalent to the barrier voltage. And at a higher voltage, since the current has gone higher, hence the energy, it takes a longer time to discharge. And remember, all these are different models to understand two different systems. We cannot see electricity. So this is one of the model that will give you an intuitive understanding of how an inductor works. For argument's sake, you'll be able to find out certain subtle differences. But still, if you take it to an analytical way, you will realize that both are nothing but a first order system. And from my electrical textbooks, I know that the time constant of an inductor is L by R. Same way, there should be an analogy in this mechanical domain, which I presume that will be moment of inertia divided by the friction. You can just check this by yourself and let me know in the comments if I am right or wrong. Now let's explore the electrical system and magnetic system analogy. The equivalent of electrical field denoted as E field in the electrical domain is H field in magnetic domain. Electromotive force is magnetomotive force. Electric current is magnetic flux in magnetic domain. Resistance is reluctance. Resistivity is relectivity. Conductance is permeance. Conductivity is permeability. You may also state E field and H field as field strength for a more accurate narration. One of the most commonly found component or parameters in electrical domain is resistance. You seldom find the inverse of resistance, conductance, being commonly used. In the case of magnetic domain, you will not find the equivalent of resistance, that is reluctance, being used so common. But you will find permeance at many occasions. Permeance is denoted by Henry per turn square. It appears in data sheets as AL value. We'll be talking about this as we go further on this discussion. Let's quickly look into this DC circuit water analogy. The cause and effect. The ratio between the cause and effect is resistance. One place it's hydraulic resistance and the other place it's electrical resistance. We saw in the case of a mechanical system or an electrical system or even a pneumatic system, the cause is the force. And in magnetic system, this force is called as magnetomotive force and is directly proportional to the current through the cable with a unity proportionality constant. That means the electrical current directly appears as a magnetomotive force for the inductor. In the case of a magnetic system, the cause is the current through the coil, and that creates the result, which is the flux. Ohm's law can be applied to any zero order cause and effect system. The ratio between the cause and effect in an electrical system is called resistance. Same in the case of magnetic system, it's called reluctance. The cause is the magnetomotive force and the result is the flux formed. Here you have the two circuits from magnetic domain and electrical domain. The Ohm's law is applicable in both the places. Rather, in any system which are analogous like pneumatic system, electrical system, magnetic system, hydraulic system, thermal system and so on. Only thing is, you need to identify each parameters correctly to apply Ohm's law on these domains distinctly. Applying Ohm's law, you can find out the current in the first circuit as the current through the circuit is equal to the applied voltage divided by the resistance. Same applies to the magnetic circuit. The current, which is flux in the case of a magnetic system, will be equal to the magnetomotive force divided by the reluctance. I told you that magnetomotive force is the force that you apply to develop a magnetic flux. If you look at the formula of MMF, you will find MMF is equal to N multiplied by I. The N is nothing but the number of turns. Actually, MMF is the current. Why this N comes in? Because when you make an inductor, you make a turn, you have X current, and the same turn once again you repeat on the same formula, you have 2X. Every time when you add up this coil, you are adding up the current. In other words, you're adding up MMF. In the case of this electric circuit, the current passing through this resistor R1 and R2 is same. Same way, in the case of this magnetic circuit, the flux formed in R core and in the R gap is going to be the same. And the potential difference drop across R1 and R2 gets divided proportional to its resistance. So if R1 is a low resistance and R2 is a very high resistance, the applied voltage goes proportionally at maximum level into R2. Same way, the applied magnetomotive force gets dropped across this reluctance proportionally to the value of this two reluctance. So if you have 1% reluctance for the core and 99% reluctance for this air gap, the 99% of the applied magnetomotive force gets dropped across this high reluctance air gap. As you know, the maximum energy, that is heat, dissipated for the same current I will be at the higher resistance. Same way, the maximum energy stored for the same flux phi will be at the higher reluctance, that is air gap. When you wind an inductor or make an inductor, generally you will be winding it on a core. A core is a substance which has got a very high permeability. This is a typical example of a core, and you are supposed to wind the coils in the center portion, and you have here, once you wind a coil in that, the magnetic flux gets two paths, which is through this high permeable medium, and the inductance formed will be very high due to the low permeability, because the flux formed will be much higher. And for a practical winding purpose, first you wind the coil onto this former and then insert your two cores from both the directions. This way. Another question we often get to hear is, can we magnetize any material? Yes, you can magnetize any material, including free space, wherein free space has got a permeability of 4 pi multiplied by 10 raised to minus 7. The materials which we can magnetize easily has got very high permeability. Like the way you will not get confused with resistivity and resistance, you should not get confused with reluctivity and reluctance, permeability and permeance, and conductivity and conductance. When you have a piece of electrical conductor with fixed size and length, you always call the resistance of that. Same way, a magnetic material which has a fixed dimension, you should always check the reluctance of that, not reluctivity. In the datasheet of magnetic components, you'll always find a parameter called AL value. This AL value is permeance of that particular core. Now let's check out a phenomena called core saturation. For explaining that, let's take out this electrical circuit as an example. Here you have your voltage source, fuse, load, and an ammeter. The current flowing through the circuit is proportional to the applied voltage, and when you keep increasing this voltage, the current keeps increasing. The maximum current that this circuit can handle is decided by the rating of this fuse. The moment circuit current exceeds the rated current of the fuse blows off, and whatever the applied voltage which was coming across this resistor becomes zero. Same way, in the case of this magnetic circuit, when you apply a magnetomotive force, the resultant flux gets formed. Like the fuse in that circuitry, this core has got a maximum amount of flux that it can handle. If you keep increasing this magnetomotive force, the flux reaches to its maximum level, and you'll find that whole effect of this inductance and the magnetic system collapse. These two circuits are not an accurate analogy, but still it gives an idea for you to understand what is an inductor saturation. When you magnetize a medium which is highly permeable, you're actually orienting the atomic particles one by one in a single direction, hence causing the net effect of the magnetism to increase. There is a limited number of these particles available for you to magnetize. Hence, once the entire atoms of a core is magnetized, there's a point beyond which you cannot magnetize. So this point is called the saturation point. These are few pictorial representation of a core saturation. This saturation depends on the core material. Like in electrical domain, different materials can have different current density. In magnetic domain, different materials can have different flux density, which is measured in Tesla or Gauss. These are examples of different materials and its magnetic saturation point given in Tesla. Also, this material property decides the frequency at which an inductor can be operated. This is basically by the property of the magnetic material, which allows the magnetic dipole to alternatively change its pole, residual magnetism that it retains once magnetized, and electrical conductivity of the material, which causes a self-induced electrical current, which is known as eddy current. Now let's understand the relationship between permeability, number of turns, and inductance. Here you have two coils, single coils, and inductance L1 and L2. Presume that they are far apart and they have got no mutual interaction. Now, if you have one inductance here and the second inductance here, the total inductance will be L1 plus L2. Now, you have another coil where you have the first turn and the second turns are sitting on the same place and they have got 100% linkage. The inductance is directly proportional to the turns coil. That means inductance goes exponentially higher to the number of turns. And here is the next case. You have the same inductance wound on a high permeable material. So you will find that the L4 and the L3, L4 will be much larger than L3. Now I told you that inductance L3 is proportional to the number of turns coiled. But what is the value of this L3? Number of turns coiled multiplied by the permeance of the space dimension. That gives you L3. So L3 is lesser than L4, and the value of this L4 will be higher by a factor of relative permeability of the core material. I have told you that AL value is permeance, but if you refer on internet, you may come across counter arguments. But if you deeply research and take out the dimensions of AL value and permeance, you will understand that AL value is core specific and nothing but permeance. Remember, it's not permeability, it's permeance of that core. And you know from the equation that AL value is inductance per turns coil. This AL value is available on the data sheet of any core. Once you have this AL value, it's very easy to rewrite the equation and find out the number of turns required for your inductance. So, turns is equal to square root of inductance by AL value. So, you get the number of turns required for you to get that inductance. Is that so easy? No. Why? Because inductance, when you design, you have few other parameters. One is the most critical parameter is inductance, and next is the maximum current that inductor can handle. And then comes the frequency response and stuff. Now, these two parameters are so very critical, inductance and current. So you cannot design an inductor without considering the saturation current of that inductor. How do we do that? Let's discuss that in the next video. If you found this video is making you understand some new concept, please support my efforts by like, share and subscribe. See you in the next video with the balanced part of this inductor design. Bye bye.